So I will be talking on basically genericity aspects of thin groups. So this work that I will be talking about is joint with Igor Rivin. And so the question, let me just write down the question very roughly, is thinness a generic property so I could write finitely generated subgroups of SL and Z, but I'm just going to, for simplicity, write for two generator subgroups of SL and Z. And so you can replace SL and Z by some other groups. I'll say, hopefully if I have a little bit of time at the end, why we start with SL and Z. So okay, so what does, so maybe before I jump into this, why ask this question? Well, it's sort of for philosophical reasons, right? So we've seen how, at least in the context of super approximation, that's really difficult to do. For example, with arithmetic groups or non-thin groups, we have known super approximation, and actually super approximation with quite a bit of extra information, such as bounds on the spectral gap, for quite a long time, going back to, say, Selberg's theorem, 3/16 theorem in 1965. Whereas for thin groups, this is pretty new, sort of dating back to just the last, at least in the full generality of it, the last century or so, with Breuillard and Gambert's L2 flattening argument from 2008, and so on. And so one might say, well, since thin groups are so difficult, maybe we just shouldn't bother because they're just too hard to deal with, and maybe they don't come up so often anyway. Well, this is, the answer to this question, as you'll see, will be basically, yes, it is a generic property. The idea is that thin groups really are the kind of group you will see most often if you venture out into the world in some sense. So they are really worth studying and looking into. So that's kind of the philosophical reason for asking this question. And okay, so what does generic mean? Well, there's various ways you can interpret this word. I will I'll describe two ways. I'll briefly describe the first, and the second is basically what we do. So the first way is combinatorial, and the second is more Euclidean in nature. Just as we had for the spectral gap, we had the combinatorial spectral gap, and then yesterday Alex talked about Archimedean affine sieve and the geometric spectral gap. That goes into that. Okay, so the combinatorial model, if you ask this question with generic being in some sense from the combinatorial model, and I'll explain in what way, this is answered completely in the thesis of Breuillard-Gelander, 2011. So the answer to this question is yes. So what does he do? What you do is you choose a finite generating set for SL and Z. You can do this. And I should say at this point that actually Owen does something a lot more general than just SLN. He considers other groups, and also he even considers not just groups inside, lattices inside of SLNR, but he considered basically any field. So quite a bit more general, but in particular this setting is covered by him. So what you do then is you choose two elements at random out of a combinatorial ball of radius y. So you take two random walks starting from identity along these generators. So, and see what you get as a result, see where you get. So I'm going to call this gamma 1y and gamma 2y be, I'll just say the random walks of length, or two random walks of length y. Again, this means the elements I get. I take these random walks starting at identity in these generators. And so then what he, the question that he considers is what is the limit as y tends to infinity of mu, or probability, that this gamma 1y and gamma 2y generate a free group. So gamma 1y and gamma 2y, the group generated by that is free. Okay, he shows that this is 1. So this probability tends to 1. And so what does free have to do with thin? So we heard a little bit about this before, but basically, so if you're a free subgroup of S ln z, so free subgroup, note, free subgroup of S ln z for n greater than or equal to 3 is infinite index in S ln z. The reason for that, so there's various ways you can see this, but since Rivin mentioned property T, Cauchy-Don property T, so it's known that that free groups did not have property T. He mentioned this. But S ln z for n greater than or equal to 3, those do have property T, and so do all the finite index subgroups of those. Now, since free groups don't have property T, they cannot be among those finite index subgroups, so you have to be infinite index if you're a free group. Okay, so you get that generically these groups are going to be infinite index. Now, thinness also contains some information, depends on some information about the Zariski closure of the group. But we also know, and now this, you can find a result like this in the literature by various people, in particular by Rivin, and also Cantor and Lobotsky, says that gamma 1y and gamma 2y generate a Zariski dense subgroup. Zariski dense subgroup of S ln with probability 10e to 1. So combining these two facts, the one that Owen proved and this together, you get that generically two elements inside of S ln z in this model generate a thin group, by which I mean exactly that the probability that they generate a thin group goes to 1 as y tends to infinity. Okay, so let me, for n equals 2, there's a little bit of extra work to be done. I'll say something a little bit about that later. So what do we, so that's the combinatorial model. This is settled by Owen. So what we do then is consider a Euclidean model, which is similar, but instead of choosing 2 elements at random out of a ball of radius, out of a combinatorial ball of radius y, we use a Euclidean ball. So Euclidean model is what we consider. And so basically what you do is you define some norm on S ln z, some Euclidean norm. You can take many norms and be okay, but we define the following norm. So for gamma in S ln z, this norm gamma is going to be the largest eigenvalue of gamma transpose gamma, so the largest singular value. And I'll call by the ball of radius y with this norm, so those gamma in S ln z such that norm gamma is less than y. Okay. And so then you can, okay, so then I'm going to define mu y to be the normalized counting measure on by. So basically so by is some finite set for any given y, and mu y of any subset is just going to be the number of elements in that set divided by the total number of elements in by. Okay, so this is a normalized counting measure on by. Okay, so just like what Owen did, then we ask, what is the limit? What can you say about the limit as y tends to infinity of mu y pairs gamma 1, gamma 2, and by? So this mu y induces a measure on by squared, such that gamma 1 and gamma 2 generate a infinite index subgroup. this infinite index in SLNZ. Okay. So we'd like to show that this also goes to 1. And okay, so a couple of remarks. Again, if we can prove this, again, results of Rivin tell us that these two elements will generate a Zariski dense subgroup with probability tending to 1. So we get the Zariski density. So that's fine. So really all we need to know is this in order to show that this group will be thin with probability tending to 1 as y tends to infinity. Now, so how do we do this? Well, even though yesterday Alan said that somehow ping pong is useless in order to, if we're showing that groups are thin, I mean, in some sense this is true. If you give me an arbitrary group in terms of its generators, it's very difficult to try to show that they play ping pong in some space. But here, really, that's all we have to use. So what we will do, so our strategy, and I'll say exactly what I mean by ping pong in a moment. The strategy is to basically replace infinite index up here by free. So infinite index replaced by free. And the way we do this is show, the way we hope to do this is show that gamma 1 and gamma 2 form a ping pong pair. Bless you. With probability tending to 1. Okay, so the idea is going to be you're going to consider the action of SLN on some space, and you're going to show that gamma 1 and gamma 2, you're going to find some regions in that space such that gamma 1 and gamma 2 do something very specific to those regions from which you can quite easily see that they cannot have, there cannot be any non-trivial relations between those two. So this is exactly the strategy that Aoun has for proving what he proves. And so how do we try to detect whether or not these form a ping pong pair or not? Well, we use a paper of Breuillard and Gelander called dense free subgroups of Lie groups, which gives a pretty nice criterion for this. I'll say in a moment what it is. So let me, I guess, set up exactly how we're going to try to detect this ping pong. All right, so we're going to consider, so we need to consider the action of SLN on some space. So we consider action of PSLNR on projective space, P n minus 1 R. Now this is equipped with a metric with some nice properties. So I'm going to write this down because I'll need it in a moment. So distance, I'll say distance from V to W in this projective space is going to be the norm of V wedge W over norm V times norm W. Okay, and this has some nice, this metric has some nice properties that will be crucial to us. So one of them is that if you consider the maximal compact subgroup of SLN, so SON, that will act by isometries on this space, on this space with this metric. So that's going to be one nice thing. I'll mention another nice thing in a moment.
What is wedge in this context?
So just exterior product. Yeah. Yeah. So just pick, a generic I'll take the elementary basis E1 through En and write V and W in terms of those and just write out the exterior product. Okay, so let me now say what it means for two transformations in SLN or PSLN to form a ping pong pair. So A and B and PSLNR form a ping pong pair if for G equals A, B, A inverse, and B inverse, one has the following is true. First of all, you have that G is epsilon contracting for some epsilon between 0 and a quarter. And what does this mean? This means that there exists some fixed point, Vg, in projective space, and also a repulsive, so this is going to be an attracting fixed point and a repulsive hyperplane, Hg. So, and hyperplane, Hg, such that G takes the outside of the epsilon neighborhood of Hg into the epsilon ball around Vg, such that G maps outside of epsilon neighborhood Hg into the epsilon ball around Vg. Okay, so you need this true for all of these A, B, A inverse, and B inverse. And then you also need these guys to all be R proximal. For some R greater than 2 epsilon. Okay, and what all this means is that the distance between this fixed point Vg and this hyperplane Hg is at least R. Okay, so what we're saying basically is that by demanding this is that if you look at this epsilon ball around Vg and this epsilon neighborhood around Hg, those are far enough apart that those do not intersect. Okay. And then finally, you want that everything's not only are these two things separated far apart, but everything corresponding, all the Vg's and Hg's corresponding to all these elements apart from each other. So you want that Va and Va inverse are at least R apart, again with this R greater than 2 epsilon, from the repulsive hyperplanes HB and HB inverse, and vice versa. So also the same thing for VB and VB inverse, far away from HA and HA inverse. Okay, so that's what it means to be a ping pong pair. And again, Aoun uses exactly the fact that generically 2 elements in that model form a ping pong pair, along with a theory of random matrix products, which we do not have, in order to prove what he has there. Okay, well, and so he is able to show that generically 2 elements in this model do form a ping pong pair. Now, the problem for us, though, is that this isn't going to work. That it's not true that in this model, 2 elements chosen at random in this way will generically form a ping pong pair in this sense. Okay, so it's not true that 2 elements chosen at random in our Euclidean model form a ping pong pair with some sort of large probability tending to 1. So let me outline what kind of goes wrong and say what you can do to basically fix this issue. Okay, so where it's going to go wrong right off the bat is that it's not going to be true that 1 element chosen at random out of this ball of radius y is going to be epsilon contracting. So let me show how you would show that. So first of all, recall that SLNR has a Cartan decomposition, KAK. This can be written as KAK, where this K is the maximal compact subgroup. So it's SONR, and A is diagonal. So I'll write this. This is going to be the set of diagonal matrices, which I'll denote the diagonal matrices by e to the j 1 through e to the jn, where the sum of the ji's is 0, and j1 is greater than or equal to j2, greater or equal to so on, greater or equal to jn. Okay, so first of all of these guys are going to be positive. They're going to be the singular values. If you want to look at again, and what is this decomposition, these are the singular values of that element. And they're ordered in decreasing order like this. Okay. So in this language, what Breuillard and Gelander show, and I'll sketch out one direction of this theorem because it's going to be instructive, is that if you have a G in SLNR and an epsilon between 0 and a quarter, then E, so this is going to give you basically a condition for which, or in fact a necessary and sufficient condition for G to be epsilon contracting. So if you look at e to the j2 of G, so that's going to be the this entry in this diagonal, the second entry in this diagonal matrix when you write this down for G, minus j1 of G. So this is the ratio between the top two singular values. This is less than or equal to epsilon squared if and only if G is epsilon contracting. Okay, so to check if this is epsilon contracting in this sense, you just look at the ratio between the top two singular values. And in fact, you can say once you have an epsilon contracting element like this, you can specify exactly using this KAK decomposition of G what a candidate fixed point and hyperplane will be. So, so if you write G as KG times AG times KG prime, then you can take VG to just be KG of E1. So E1 here is just the vector 1, 0, 0, 0, 0. And HG is going to be the span of KG prime inverse of EI. These are the other elementary basis vectors for I equals 1 to 2. Sorry, not 1 to 2 to n. Okay, good. So let me just sketch out. One direction of this is much more difficult than the other. But the direction of, so if you have this this ratio between the top two singular values, then your element is contracting. That's something that I can do pretty quickly for you. So let me write that down, why that happens. Okay, so this is just going to be the proof of this direction. So if this, then epsilon contracting. Okay. So first of all, note, because, and this is something you can see pretty quickly, if you think about it, because I told you that this K, the SONR, acts by isometries on this space, you can actually assume that your element G is diagonal. So the K part is not going to do anything. Okay, so can assume, since K acts isometrically, on this Pn minus 1r, that G is diagonal. I'm going to write it's A1 through AN. Okay, so and then suppose I have a point V in Pn minus 1r, which is outside the epsilon neighborhood of Hg. Okay, so what that means, so such that the distance from V to H is greater than or equal to epsilon. Now, what is this distance? Well, another nice thing about this distance is the following, that if you look at the distance from some point V to the kernel of a linear form from Rn to R, which this Hg is, kernel of F, where this is a linear form from Rn to R, this is going to be this is just going to be the absolute value of f of v over norm f times norm v. Okay. So here, what we're going to get is this is just going to be, so f of v in this case is just going to be the first coordinate of v, so I'm going to call that v1, and then over just norm of v. Okay, so that's what it means for v to be outside the epsilon neighborhood of hg, is this. So this is what we're given, and now we want to show that g maps that v is mapped by g into the epsilon ball around vg. So let's then consider the distance from gv to this. All right, so by the way, the hg and vg I'm taking here are the ones I wrote up here. So to this vg, so in this case, I've taken g to be this diagonal matrix, so this kg is just simply identity. So we just have E1 for the vg, so to E1. Okay. And so what we get is just from what the norm is, this is going to be gv wedge E1, norm of that, over norm gv times norm E1, which is 1. And now the observation is that if you look at this thing here, norm gv wedge E1, so gv is just simply, since g is diagonal, it's just simply A1, V1, A2, V2, A3, V3, and so on. That's that vector. And so if you look at this, this is going to be less than or equal to A2 times the norm of V. Because what happens when you take your product with E1 is basically the first, so you have, this is going to be, this GV is going to be A1, V1, E1, plus so on, plus AN, VN, EN. And this first part with the A1 coefficient here is just going to get swallowed when you wedge with E1. It's going to go away. And then the largest next singular value is A2. And so this is going to be bounded above by A2 times the norm of V. Okay? Similarly, in a similar way, this thing here is going to be greater than or equal to A1, V1 in absolute value. Okay. So these are pretty routine things to check. And so then combining these two things, you get that this is less than or equal to A2 times norm of V over A1 times absolute value. V1, A1, and A2 are both positive. We can assume. So, okay, so we have this. And so what do we have? Well, this norm V over V1, we know this is greater than or equal to epsilon. So this part here is less than or equal to 1 over epsilon. And this part, by what we have assumed up there, is less than or equal to epsilon squared. So altogether, this is less than or equal to epsilon. Okay, so that's the proof of that. Any questions at all? All right. Right. So the first thing we're going to do in order to check whether generically this gamma 1 and gamma 2 are going to form a ping pong pair is check whether generically an element chosen at random out of a ball, this ball of radius y, is going to be epsilon contracting or not. So is a generic gamma in S on Z, and by which I mean in this language, so you choose gamma uniformly at random out of this ball of radius y and then let y grow, see if the probability that this is epsilon contracting goes to 1 or not. So epsilon contracting for some epsilon between 1 1/4. And so what you do in order to see this is you need to evaluate the following ratio. The number of gamma and by, which are epsilon contracting, over just the number of points in by. Okay, so this is some counting in S ln Z. And what we do in order to evaluate this is instead work inside of S ln R. It turns out to be easier. So consider instead the integral. So I'll define, so we'll take the limit as y tends to infinity, right? Because this is what we want to do here as well. We want to take the limit as y goes to infinity. Integral over regions I will describe in a moment, ry prime d mu. D mu is going to be Haar measure over S ln R, and then integral over r sub y d mu. Okay, so let me define all of these things I've written down here. So ry is defined by, well, so this is going to be corresponding to the ball of radius y. It's going to be the elements in S ln R of norm less than y. And so norm for us is determined by the top singular value, the largest singular value of gamma. So this is going to be defined by the following things. So you want e to the ji is going to be less than or equal to y for all I. Okay, remember this is, so if you write down e to the j1 through e to the jn, those are the singular values. And also sum of ji is 0, j1 less than or equal to j2, sorry, greater or equal to j2, greater equal to so on, greater or equal to jn. Okay, and ry prime is just going to be the intersection of ry with basically this condition that the top two singular values have a large ratio, which I'm going to write as j1 is greater or equal to j2 plus t for some fixed t. Right, because this is exactly what it means for e to the j2 over e to the j1 to be less than this epsilon squared. You just fix some t depending on that epsilon. Okay, so and what is mu? So this d mu is Haar measure on S ln R, and let me write down what that is really quickly as well. This is the product from so k less than I between 1 and n, and then sinh ji minus jk d j1 through djn. Okay, so the really nice thing about this Haar measure is it's defined in terms of these singular values, and these regions are also defined in terms of those singular values. So these integrals are quite doable to compute.
Those just measure on the diagonal, right? And then you put coordinates. Then you put Haar measure on the 2k pieces. Because anyway, the regions are independent of they're by k invariant.
Yeah. Right, this is, well,
The j's are the coordinates
yes.
of the diagonal.
Yeah, so that is what the Haar measure is determined by completely on S ln R. So.
But then you can put it, yeah. Then you put Haar measure on the compact parts on either side.
Well,
Like probability. Okay.
yeah, so yeah, in the end, the k's are going to matter. What happens with the k's and the measures there are going to matter. But right now, this is all that we need. So this is the how measure on SLNR, what how measure on SLNR is. Okay, so with this, what we get, and so by the way, once you determine what this ratio is, it turns out you can look at Duke, Rudnick, Sarnak, or also Eskin, McMullen. This will tell you that this ratio here is asymptotic to the ratio above, as y tends to infinity. So this brings us back to SLNZ. Yeah, the point is we work in this SLNR setting, and that basically tells us what we need about the SLNZ ratio up there. Okay, so once we evaluate this, what we find is the following. If you look at this limit here, then it's going to be bounded above by 1 over e to the t times n squared minus 3n plus 2, and greater than 0. Okay, so if you plug in 2 into this, you're just going to get 0. So this is just 1 for n equals 2. So that doesn't tell you that much. It just tells you this probability is between 0 and 1. But as n gets larger and larger, you see, so as soon as n is 3, this is no longer 1. It's something less than 1. And as n gets larger and larger, this gets smaller and smaller. So in particular, you have that this probability that that an element in SLNZ's epsilon contracting is going to be positive, but it's not going to be tending to 1 as y tends to infinity. Okay, so that's going to be a problem for our hope of showing that two elements form a ping pong pair with probability tending to 1. Okay, we can, though, so n equals 2 is not a problem. So in that setting, with this setup, you can show what we show, that two elements chosen at random out of SL2Z do form a ping pong pair. So what we show is that limit by gamma 1, gamma 2, and by squared, which gamma 1, gamma 2 are infinite, generate an infinite index subgroup in SL2Z. This is going to be tending to 1. And so let me just say a little bit how we do this, because so what we do is we show that these two generate a free subgroup of SL2Z with probability tending to 1. But being free in SL2Z is not enough to be infinite index. You do have free subgroups that are finite index. However, using the fact that this is free, that this is a Schottky group, in fact, we use some upper bounds of Beardens on Hausdorff dimension for Schottky groups to show that generically these elements are going to generate groups of arbitrarily small Hausdorff dimension. So given that, once you have arbitrarily small Hausdorff dimension, you automatically have infinite index. So in some sense, we show that not only are these elements going to generate thin groups with probability tending to 1, but they're going to generate very thin groups with probability tending to 1. Okay. So what about n greater than 2, though? Well, we can salvage the situation there. So salvage the n greater than 2 case. And so maybe just let me kind of motivate this. One of the key differences between our model, this Euclidean model, and Aoun's model is the following: that if you consider the combinatorial ball of length y, of norm y, and you choose and you look at some element gamma in there, so it means the word length of that element in terms of the generators is at most y. Its inverse is going to have the same word length. So its inverse will also be in that ball. That is not generally true for our ball. You can have an element gamma with a small top singular value, but when you take its inverse, it'll have a very large top singular value. So its inverse might not be in the ball. So the idea is to symmetrize the ball in order to make it more like the combinatorial ball. So I'm going to define a new ball, by prime. This is going to be by intersected with gamma in S(ln) z, for which the norm of gamma inverse is at most y. So this is actually a zero density subset of by, but it's a pretty natural kind of ball to consider. And again, we're going to choose mu y prime to be the normalized counting measure on by. On by prime. Okay, so then we are able to show what we want. That the limit as y tends to infinity, mu y prime of gamma 1, gamma 2 and by prime squared, such that gamma 1, gamma 2 generate a free group. This tends to 1. Okay, so what happens is that it's, again, not true that if you choose an element uniformly at random out of this ball, you will have a large ratio between the top two singular values. Okay, but what will happen is that you will generically have a large ratio between the middle two singular values. And that happens to be very good because, in particular, the inverse, remember, we need both gamma and its inverse to be epsilon contracting. So the inverse will also have this large ratio in the same spot between the middle singular values. And okay, so then what we do is we do the same trick. So we look at the integral over the ratio of integrals over these two different regions, but the regions now are slightly different. So let me just write this here. So instead of letting this ry be defined this way, we'll just put an absolute value here to say that this guarantees that the element and its inverse have norm less than or equal to y. And then here, instead of j1 greater or equal to j2 plus t, I'm going to consider the situation where j n over 2 for n even, and you would take n plus 1 over 2 for n odd, but since I'm running low on time, I'll just focus on the even case. So n over 2 is greater or equal to n over 2 plus 1, jn over 2 plus 1 plus t for some fixed t. Okay, and so then what you get is that when you look at this ratio, this is going to be tending to 1 as y tends to infinity. Now, why is that so good? I mean, didn't we need a large ratio between the top two singular values? Well, so let me write this down here. Instead of considering the action of S(ln r now on this Pn minus 1r, on this projective space here, you consider its action on a projective space of a larger dimension. Okay. Okay, so consider S(ln r, the S(ln r acting on now the projective space of the n over 2 exterior even, it'll be n minus 1 over 2 for n odd of Rn. And what happens then is then you get if you look at this action, you will get a large ratio between the top two singularities in the following sense. So here, let me just say what happens is you're going to take the point then in the fixed point in this space to be just your kg. So again, you take this decomposition of g, kg, ag, kg prime, and then you take this to be kg times, this is the first elementary basis vector, and then if you look at the basis for this, which is going to be E1, so basically all possible exterior products of n over 2 of the elementary basis vectors. That's going to be the basis. So I'm going to take this to be E1, wedge so on, wedge En over 2. And then here, this is going to be the span of the rest of the elementary basis vectors for this space. Then what will happen in this proof is once you get down here, so everything will basically stay the same. And then once you get down here, if you look at GV, wedge this first elementary basis vector, you're going to get that this is at most, this is going to, instead of A2, you're going to get this is at most A1 times so on times A n over 2 minus 1 times A n over 2 plus 1. Okay. Times this norm V. And here you're going to get that this is going to be greater or equal to A1 times so on times A n over 2 V1. And again, when you look at the ratio, what you're going to get is exactly the ratio between A n over 2 down here and A n over 2 plus 1 up there, which you will know from this from this argument is less than epsilon, less than or equal to epsilon squared with a high probability. Okay, so I'm rushing a bit at the end, but the point is that this gap in the middle now guarantees that you do put, that your element is going to be epsilon contracting when you consider the action on the correct space. And you can finish off the whole thing and prove that, in fact, it'll also be R proximal with probability tending to 1, and that the two elements will play ping pong with probability tending to 1. The R proximality follows by, so basically now R proximality and all that depends completely on the K component, because these fixed points in repelling hyperplane are defined completely by the K component. And so what we use there is equidistribution in sectors by Gorodnik and O. But okay, so we are able to prove generic thinness in this slightly modified Euclidean model. And I'll just finish by saying that once you do this for SLN, if you want to do this for some other semi-simple Lie group, you can do this in a very similar way. So this paper of Breuillard-Gelander, they work all this out for SLN, and they know that you can take a representation from some other Lie group into some SLN and just work within SLN to show that your group is free that way. And in fact, 2 graduate students at UIUC, Sneha Chaubey and Amit Amal, are working out that now. Okay, so I'll stop there.